Good morning, everyone. I'm Jingtian. I'm hosting this event together with Kewang Nan from the MIT. I'm at the UCLA. Welcome to the Martlets Talk. And today we will have Professor Wubin Bai from the University of North Carolina at Chapel Hill to give us a talk, Heterogeneous Integration of Bioelectronics Materials for Smart Health. So just to give a little bit introduction to ourselves, we're the Martlets Society, and our mission is to give young scientists at a very early stage of their career the opportunity to give talks and make more impact. So and it is also our goal to let these different scientists from different research background to come together and get exposed to other areas and accept multidisciplinary research collaborations. And we have three types of research. The first is the most common one, the Martlets Talk. The second one is the non-academia WBA talk, and also the TMS workshop for skills and technique development. And here's the talk agenda today. I'm almost done with the opening today, so I will hand over to the speaker introduction, Dr. Kewang Nan. But just before that, let me give a short introduction on how we do the Q&A. So during the talk, feel free to write your questions in the Q&A chat, so we can keep track of your questions. And you can raise time at the end of the talk during the Q&A to draw our attention. And also, please, for each turn of the asking questions, please limit yourself to 2 questions. And Kewang, all yours.
Okay. Thank you, Jingtian. It's my honor here to introduce Professor Bai, who obtained his BS degree in physics from USTC. And then he went on to MIT, do a PhD in the Department of Material Science and Engineering. After that, he was a postdoc in Professor John Rogers' lab, first at UIUC, and then at Northwestern, where we had over for like 2 years. And he's currently a assistant professor in the Department of Applied Physics, Physical Science at University of North Carolina at Chapel Hill. So his lab focuses on heterogeneous integration of soft materials and nanomaterials to design and develop devices for healthcare. So personally, I know Professor Bai very well. We sort of work on multiple projects when we were both in Rogers' lab, and he is very knowledgeable on many things like material science and microfabrication. And also he's on a personal level, he is very like collaborative and open-minded to work with. So with that, let me hand over to Professor Bai to start his presentation.
Thank you very much, Kewang and Jingtian, for the very kind introductions. I have to say I'm grateful for these opportunities, and also it recalls me when I studied postdoc, Kewang taught me lots of important techniques which set up the foundation of some of the research we will talk about here. So I'm already very grateful at the beginning and also now. So let me share the screen. Cool. Thank you everyone for coming to the talk. It is a great pleasure to interact with world-class experts, leaders, and especially the young talented researchers here. So in the next 40 minutes also, so I want to present some research emerged from a visionary concept about making electronics dissolvable or partially dissolvable. So we will explore how such endowment of unconventional property to the electronic system could open up new opportunities in the medicine and biomedical research. Okay, so the first question you might ask is why we want to make electronics dissolvable or disappear. So we see recent breakthroughs have made electronics adopt soft mechanics, which give them adaptive freedom in space to conformally interface with living tissue. But being adaptive in space is not enough, as most biological systems are dynamically evolving. So to fully realize a seamless integration at the human-machine interface, the next generation bioelectronics needs to be adaptive both in space and time. And that drives an expanding research effort in dissolvable electronics or transient electronics. But what could be the potential impacts for dissolvable electronics? So we see for many disease treatments, the essential sensing and the stimulation sites are located inside the body, which in many cases require an invasive approach to access. However, the challenges which also frustrate the medical field is a strong materials mismatch at the abiotic interface. For example, when a rigid electrode is inserted into a soft brain tissue, tissue damage and a scar formation may happen. When a metallic surface contacts biofluid, then the corrosion may appear, which could disrupt neuron functions and the normal metabolism. Also, many of the disease treatments are only temporary. Therefore, implanting a permanent device could even bring more complications and risks. So those unmet clinical needs motivates an emergence of a new type of electronics that could provide a dynamic and compatible interface with living tissue and then safely dissolve as part of a metabolic circle after completing their diagnostic or therapeutic duties. And the preliminary previous research primarily focused on using those electrical mechanisms for transient systems, ranging from thermal sensors, blood flow sensors, electrical stimulators, and the drug delivery system. They provide great functionalities, but mostly unable to achieve multiplex capability and adaptation-based application. So this presentation will aim to describe our recent efforts on designing integrated systems that leverage unique property of each material component. So in this talk, we will first focus on transient materials and their interfaces with living tissue. And then we will talk about two application paradigms based on system-level integration of heterogeneous materials to highlight its potential in sensing and stimulation. So first, let's start with the fundamental behavior of transient materials or bioresolvable materials. So here we focus on using those nutrients or biomaterials, including organic polymers and the inorganic nanomaterials as building blocks for making bioresolvable electronic and photonic system. So semiconductor is only a starting point. We have to think about dielectrics, conductors, substrates, and the processing approaches to integrate those materials together and build a functional system that can leverage each material components. So as we know, silicon is a foundational materials for modern computing electronics and photonics. Traditionally, they are rigid and unbendable. If we scale down the dimension of those silicon structures, their mechanical rigidity will scale down accordingly. Eventually, the silicon nanomembrane can become highly flexible. On the other hand, silicon can undergo slow hydrolysis reaction in aqueous environment, such as the biofluid in our body. So we developed a soft lithography approach that can integrate silicon nanomembrane with a block-polymer film. Therefore, we are able to make the silicon nanomembrane hybrid system dissolve in biofluid within a certain period that can match with various medical contexts. And this period can be tailored through encapsulation strategies and the molecular engineering approaches, so which I will provide more details throughout this talk. So the deeper question we would like to ask is how these transient materials interface with living tissues. So here we show a parody of in vivo bioresorption study on silicon, which is representing materials and enable the approach to set up the landscape that bioresolvable electronics can build upon. So the computed tomography reveals the gradual bioresorption of silicon nanomembranes implanted into subcutaneous region of mouse. So at this dissolving timescale, we want to know where those dissolving silicon elements transport inside the body. So we use a spectrometric analysis on each explanted organ to quantify the biodistribution of elements dissolved from the implanted devices. As you can see, heart, muscle, and blood experience accumulation of silicon at the initial implantation stage, but still within physiologically normal range, and then gradually decrease to previous level, suggesting normal metabolic clearance of silicon through the body. So both complete blood count and blood chemistry analysis show normal healthy status of the mice during the 7-week implantation period, indicating no observable toxicity resulted from the bioresolvable devices. So the next question we might ask is how the device implantation affects the neighboring tissues. So here we implant a silicon nanomembrane into the brain of a mouse, and using the immunohistochemistry to understand the cellular status. So we see minimum inflammatory glial responses on day 1, which is normal for a typical surgical implantation. And then these responses gradually decrease to levels comparable to control group, suggesting normal recovery of mice from the implantation surgery. So the cross-sectional area of the implantation site shows a consistent decrease of the implanted material over time, indicating a bioresorption with no sign of adverse effects to the neighboring neurons. So those studies of transient materials project new possibilities in medicine and biomedical research. So here we will explore the application potentials and the associated design pathways by describing 2 examples. One focuses on sensing, the other focuses on stimulation. So the first one is about spectroscopic sensing system for the brain that are implantable and minimally invasive, like a surgical needle, with improved sensitivity and more functionalities. And the user cases on treatments of hydrocephalus, intracranial hemorrhage, and ischemic stroke, which requires continuous monitoring of intracranial oxygenation, temperature, and neural activity of the brain during recovery period. Existing tools often induce surgical complications, inaccurate detection, and side effects. So our goal here is to design a bioresolvable optical proofs to enhance diagnostic precision, minimize additional risks, and eliminate secondary surgery for device extraction. So the active sensing regions supported on a PLGA substrate consists of 3 key components. The first one is a bioresorbable fiber made of PLGA FDA approved biopolymers for delivering light with a certain wavelength to the sensing proofs. And the second is a bioresorbable photodetector made of nanomembranes of doped monocrystalline silicon for generating electrical signals in response to the transmitted light. And the last component is the electrodes made of thin films of zinc for electrical readout. We also use a thin layer of silicon dioxide for encapsulation to ensure stable performance over a control period, which is followed by a full device bioresorption. So we produce those bioresorbable fibers based on a simple drawing process, applied to the bulk preform heated to temperature around 200 degrees Celsius to yield the PLGA core. And we can use a tip of a commercial fiber as a lead for the fiber drawing process, which directly couples the resulting bioresolvable fibers to the commercial fiber in order to minimize decoupling loss at the junction areas. So without an encapsulation layer, it takes around 2 weeks for typical bioresolvable optical proofs to fully dissolve. Adding 200 nanometers amorphous silicon dioxide layers can effectively prevent the penetration of biofluid into the active electronic components and maintain stable performance over 10 days before undergoing bioresorption. So for the current device shown here, we use a doped silicon nanomembrane as a photodetector, which relies on a tunable laser as an external light source to realize spectroscopic sensing over a wide range of wavelengths. So in the next example, we replace the silicon nanomembrane photodetector with a tricolor silicon photodetector. Therefore, we only need a low-cost white light as an external light source to enable a simple spectroscopic sensing simultaneously and continuously. So the idea is based on the wavelength-dependent penetration depth inside silicon, where the red light with a long wavelength can penetrate deeper, and the blue light with a shorter wavelength can only penetrate shallow depths of inside the silicons. So if we dope the silicon layer by layer to form a vertical stack of alternating NP-NP dope regions, we can obtain 3 photojunctions at those interfaces. Each of them shown is a peak sensitivity at a distinct wavelengths. So based on the measurements of the 3 junctions, we can calibrate the sensing signal and provide a simple spectroscopic sensing capabilities. So we integrate the tricolor photodetector into the bioresolvable optical proofs and implant the proofs in the brain of freely moving mice near the parietal loops. The high mechanical flexibility of those connecting wires allows the mice to move relatively freely inside the housing cabinet, so suitable for certain behavior studies. The cerebral oxygenation is a diagnostic indicator for various neurological diseases, such as intracranial hemorrhage. So implanting the device can enable us to monitor the brain oxygenation of a freely moving mouse as the 3 sensing wavelengths are well positioned at those sensitive regions, where oxygen saturation influences the light absorptions. So based on Beer-Lambert's law, we can calibrate the brain oxygenation by comparing the photocarbons of the 3 junctions and enable a continuous measurements with precision comparable to clinical standards and with the advantage of a much more localized detections. So the third type of bioresolvable spectroscopic sensing system is based on the optical filter made of multi-stacks of alternating layers of silicon oxide and silicon nitride supported on a PLGA biopolymer films. So the whole system is bioresolvable and mechanically flexible, even for the 30-layer films with a minimum bending radius around 300 micrometers. So by controlling the periodicity or a combination of zero periodicity, we can modulate the transmission spectrum through the optical filter in a design manner. So using the multi-layer platform, we can create a diverse range of optical filtering capabilities, which can be useful for applications such as fluorescence imaging, optical control system, and optogenetics. So in this case, we have a bandstop optical filter with a blocking wavelength around 500 nanometers across a wide range of light instance angle, making it capable for detection of fluorescence-based calcium indicators of neural activity. So we integrate the bioresolvable optical filter into the transient optical proofs. And when the proof is immersed into a green fluorescent solution, and the fibers delivers blue light, the photodetector embedded underneath the optical filter can only respond to the emission of green fluorescence light, which is proportional to the concentration of calcium ions, an important neuron indicators. So the proportion is in a relatively linear fashion and relevant to the physiological range in animal brain. So we can use such optical proof to detect neural activity with a high spatial temporal resolution and find out the suppression of neuron firing events in response to external anesthesia treatments. So our next generation of implantable optical proofs focuses on cardiac monitoring. And the user cases of is for the large cohort of neonates who were born prematurely and often suffer from cardiac complications. So we see the existing tools often require relatively rigid wires tethered to a bulky instrument, which induce additional risks and complications to the babies, especially the baby tends to move around when they are awake, and that may generate additional tissue damage. So we design an implantable cardiac proofs that integrates wireless communication technology based on Bluetooth low energy to transmit sensing information wirelessly. And we use the microscale LEDs and the photodetectors at the tip of the probe instead of using the traditional glass optical fibers to further enhance the mechanical softness of those connecting wires to further minimize the tissue damage. The device consists of two key components. One is a soft sensing proofs, which houses the micro LED and the micro photodetectors at the tips, and that will facilitate a minimally invasive implantation to reach the cardiac surface. And the other is a Bluetooth module, which is fully encapsulated by a layer of medical grade silicone and will be implanted at subcutaneous region of the body. So our in vivo study demonstrates its capability in sensing pulsation patterns and detecting subtle change in tissue oxygenation with precision comparable to a commercial available catheter sensors based on the optical glass fibers. So we also use a mouse model to simulate events of hypoxia and arrhythmia for validating the sensitivity of implanted optical proofs. The sensing information shows the change of pulsation patterns and oxygenation levels in real time, which can be used as early signs for carry on immediate therapeutic treatments. Okay, so the last example in the sensing system focuses on the flap monitoring, and the user cases is on reconstructive surgeries or transplantation surgery, especially for the muscle flap or internal organs. So the recovery stage is equally critical as the surgery itself, and it needs very close monitoring to ensure a smooth regrowth of the transplanted tissue and the successful reconnection of blood vessels to the neighboring vessel. So current clinical settings mostly rely on skilled personnel to check the recovery status constantly for certain deep tissue surgeries, which may not be feasible for low resources settings. Therefore, there are critical unmet needs to have a low-cost intramuscular proofs, which can monitor status of the muscles or internal organs continuously and in real time. So we further miniaturized our previous design to enable the probe to be injectable into the muscles. And different from the previous design, we use two photodetectors in a single sensing proofs to form a spatially resolved spectroscopy, which further enhances the sensitivity. Also, the proofs incorporates wireless communication technology, which improve user comfort and minimize additional risks. So we use a thin layer of parylene to fully encapsulate the proofs in order to prevent penetration of biofluid into the electronic components, which will ensure the longevity of the device performance. And also we designed the barb-like structure made of bioresolvable polymers that can be attached on the backside of the proofs to minimize relative motions at the implantation site by anchoring the proofs to the neighboring muscle tissues. So for stabilized sensing and also to facilitate an easy extraction of the device once the barbs are fully dissolved. So we collaborate with a plastic surgeon who provides the porcelain models. So the picture looks a little bit bloody, so I will quickly fast forward. And so in summary, he could raise the active rectus abdominis muscle and allow the proof to be injected into the muscle. So by clamping the artery and veins separately, we can create simulated events of ischemia and congestion. So here we show the device can capture the subtle change of oxygenation associated with ischemia and congestion. And the sensing responsivity from the probe is comparable with a skin-mounted commercial device called Optics. And the skin-mounted device can only detect oxygenation change around the skin level. So if the reconstructive surgery focuses on the muscle-only flap, then the intramuscular probe we design here become the only choice for this case. So we use a similar strategy for detecting oxygenation levels of internal organs. So here we use a porcine model as well and inject an implantable probes into the kidney. So we could use a tube for clamping the arteries and the veins individually to create kidney ischemia and congestions. So the measurements further demonstrate the capability of our device to capture subtle change of oxygenation levels inside kidney tissue, which cannot be easily accessed by traditional commercial devices. So if we transform the raw data from its original real space into a frequency space, we can then visualize more physiological signals or patterns, including the heart rate, breath rate, and their dynamic variations. All of them could reflect certain diagnostic informations about the recovery status after the reconstructive surgeries. So another key features to highlight for the implantable probe is the integrated bioresolvable parts, which anchors the device to the implantation site for enhanced biocompatibility and sensing stability, as confirmed by the computational tomography. So in comparison, the device without the barb structures shows strong movements inside body over the implantation period, which is unwanted in most cases. So after the barbs are fully dissolved in biofluid, the device can be conveniently extracted from the implantation site with minimum damage to the neighboring tissues. So previously, we discussed about integrated bioresolvable sensors that can enable real-time optimization of therapeutic procedures. So in the final section, we will briefly talk about transient stimulators that may have potential to facilitate tissue regeneration. So in tissue engineering, there are significant amounts of study on how electrical field can facilitate cellular migration and proliferations, which are two essential factors to influence wound healing. So this is especially critical for certain patients with diabetics who often suffer from inefficient or over-delayed wound healing process. So the existing commercial tools use two gigantic pads attached on normal tissue near the wounded area, which is inefficient and may bring complications to normal tissues. So the goal here is to build a transient stimulator, which can wirelessly provide stimulation and form a benign and precise interface with a wounded area. So our design consists of two parts. The first one is an energy harvester based on the near-field communication technology to provide desired electrical powers, and the soft bioresolvable electrodes that can directly contact a wounded area to generate uniform electrical field that is designed to align the cellular migration pathways. So we also use such serpentine design schemes for the molybdenum nanomembranes, which is bioresolvable and also provide tissue-like mechanics to further minimize potential adverse effects to the neighboring tissues. So as shown in the preliminary in vivo study using a mice model, so the wireless transient electrode stimulation can effectively accelerate the wound healing process compared with the control group. So as the wound heals, the regenerated tissue will gradually bury the transient electrodes, and then we can detach the energy harvester electronics from the patch to complete the treatments. And we envision the transient stimulator could serve as a detachable patch that can form a direct contact with the wounded area without compromising the patient comfort. So in summary, with the exploration of synergistic properties between soft materials and nanomaterials, as well as heterogeneous integration. So we aim to innovate a bioelectronic system for smart healthcare with a real-time optimization and novel interface with the living tissues and cells. So in the end, I'd like to thank my mentors, both as my postdoc stage and PhD stage, collaborators and teammates. Much of the work present here relies on strong multidisciplinary collaborations and discussions with experts from different fields. And also we are a relatively young labs. If I interested in get connected, so please stay in touch and consider sending me an email. And so finally, I'd like to thank the community for the opportunity to get to showcase our research, and also thank you everyone for your kind attention.
Yeah, great talk. So Professor Bai, you can try turn on the video.
Right. Okay.
Yeah. Cool. All right. The audience can see you. Yeah, this is really fascinating work. So some of these I heard about first time. So right now we can start. We can open for questions from the audience, but I would like to open with a question of my own. So your optical approach to measure biosignals are very interesting. So do you think this can be extended to other signals, like especially in the biochemical realm? For example, some sort of hormone or proteins in the brain or other organs, because those things are has been very difficult to measure using traditional electrode-based approaches. So can you comment on that?
Yeah, great question. I think it's also the focus of the research in the optical sensing field broadly, and I would say, and also the chemical sensing is also a central focus for the next generation implantable devices. And so far, most of the sensing are focused on the physical signals. So our current thinking, some potential mechanisms to enable the chemical sensing based on the optical approach is by introducing intermediate interface, which can translate the chemical stimuli to optical readable signals. So fluorescence is one option, and there's other exploration based on the stimuli responsive hydrogel, which can also translate the chemical signals into optical readable signals. So that's kind of some potential method ongoing, but I would say it's not as established as those physical sensing mechanisms so far.
Okay. Yeah, thank you. Great. So are there questions from the panel and from our audience?
Again, please type your question in the chat if you have one, or on the Q&A. I actually have a question. So, especially for these slides, is there a general strategy from the materials perspective to tune the lifetime of the bioresorbable materials? Like for this one, suppose you like different patients probably would like the bioresorbable barbs to stay there for a different amount of time, right?
Yeah.
So from the materials properties, how do you tune it to let it maintain the structure for different amount of time?
Yeah, great. So this is something we haven't expand and provide more details. And so the bioresolvable barbs used here is based on also the PLGA biopolymers, which can be further modulate by changing the general molecular weight or the ratio between the two blocks, the PLA part block and the PGA block. And by changing those molecular parameters, we can tune the bioresorption behaviors of the polymers. So that leave a capability to tune the dissolving times inside the tissue, so passively, and the time has to be set before the implantation. It depends on what type of polymers we choose, and there's there's other approach to enable active change of the dissolving time using electrical trigger or some type of nanoparticles that can absorb the near infrared light that generates local heatings that will fasten the dissolving of local polymers. And that's another approach to enable active dissolving controls.
I see. Thank you. So we got another question. Okay, so can we actually
I was wondering if the electrical stimulation through the molybdenum electrodes accelerate their bioresorption due to. Oh yes, that's a very critical questions, and so this is one important parameters I would say has not been systematically studied for the transient systems, and the electrical corrosion of such transient metals depends on the work function of the voltage, and so for the molybdenum, the work function usually around the 2 volts, and so then that was generally higher than the desired electrical voltage we want to apply for the wound healing process. And for the mice model, we are using 1 volts and in a very sharp step functions, which significantly minimize the electrical corrosions. And some type of wound healing process may require a lower amplitude of voltage. So which probably in this case won't introduce a significant amount of electrical corrosions. But I agree, that's a critical parameters, a trade-off to balance for the transient electrodes used for applying the electrical stimulation.
Yeah. So let me ask another one. If you maybe this is still early stage, but if you ever envision these things to go on to human trials, do you what are your thoughts on the FDA approval challenges on some of these because compared to traditional electrodes or devices, these things contain components that will potentially dissolve and get absorbed by the human body. So do you see any questions being asked by reviewers or from other like during your interview about those? And what are your thoughts on those?
Yeah, a very critical question, and also especially for the transient electrodes to be used in practical settings. So far, I would say it probably still takes a long process to reach to a mature stage for FDA approvals. And there's probably a feasible way is to use some of implantable electronics like pacemakers and choose the metallic materials used in those already approved systems for such electrical stimulation patch. That may be feasible to get a smooth process for FDA approval. But molybdenum as implantable metals, it has been not yet fully utilized in the clinical settings, but mostly in the academic research stage as well. And some of the FDA-approved implantable electronics using gold metals, which probably because the high stabilities inside the bodies, but it's not degradable. So maybe for the skin wound, it could be further used for the gold membranes as well. So that's just a thought. Yeah.
Great. So I saw someone join the panel. Is it Zehao? Do you have a question or?
Yes.
Yeah.
Yes. Thank you. So very nice talk. So I was wondering, how is the semiconductor material resolved in the body, like silicon or silicon oxide?
Yeah, cool. And so silicon as a transient materials was realized or discovered like about 8 to 10 years ago from the postdoc groups I was fortunate to be studying. And so the findings is based on the hydrolysis reactions of silicon, and because the reaction rate is extremely slow. So, and previously we all using silicon as a bulk materials, silicon wafers, usually with a thickness around 500 micrometers. And then compared to such a scale, and the dissolving behavior in the waters is almost negligible. So, and then the very early stage studies, they use silicon nanomembranes, which is the thickness around 200 nanometers. And then it's feasible to observe the thickness variations when such materials is immersed into a aqueous solution, or maybe the PBS solution to be more relevant to the human bodies. And then the dissolving rate is not significant. It's around maybe 10 nanometers per day or 100 nanometers per day, depends on the composition of the biofluid. So that set up the dissolving time scale for such silicon nanomembranes, which means if we want to treat silicon as a bioresolvable materials, we have to design such device in the context of its dissolving behavior. So if it's 200 nanometers, it may dissolve within a couple of months, maybe a few weeks. That can be used as a transient materials, but 500 nanometer silicon wafers to put in the bodies, maybe it takes 200 years to dissolve. That more than a lifetime, probably. So, then it cannot be treated as a transient materials.
Thank you.
Yeah, critical point.
Great.
Kewang. Yeah, I have a question to Professor Bai. Sorry for my background noise.
No worries. Happy noise.
Yeah, I have a question about the optical sensor, like using bioresolvable microstructure to like avoid any like tissue artificial like artifact motion, things like that, right? I'm wondering. Yeah, I'm not sure which page. Like it's a kind of unpublished paper, I think. Not that one, probably. Yeah. Anyway, so that one. Yeah, that one. So I think you may integrate some like a optical sensor to like for biosensing, right? I'm wondering if this kind of like bioresolvable bulbs dissolved in the body fluids, will they affect the optical transparency of your device? Like
Yeah, great question. So we have that's attention to detail. So we observed such at least a baseline shift. So when the surrounding environments is in a dynamic process, meaning especially the bulbs are dissolving. So it probably first swells a little bit, and such swelling will change the refract index of the bulbs, and then the whole environment is kind of changed. So it will shift the sensing baselines, and which is observed from the initial experiments. So that means if we want to use a proofs for long term, it's the current some of the previous design strategies may have limitations. So and then that's advantage of using two photodetectors. Which can cut off the baseline shifts a little bit. I would say extensively. But still, you could the environments of the two photodetectors experience also slightly has a variations, and that variation may contribute to the baseline shift. If we sense this, use these proofs for a long period, a few days, we may see a slight shift of the baseline, and it requires calibration mechanisms, and also that's kind of a limitation applied to some of the even commercially available optical sensors. It requires calibration steps after a long-term studies. So that's kind of the strategies we are using in here. Yeah.
Thank you.
Great point.
Thank you.
Okay. There are any other questions? If not, maybe we can just end here and let Jingtian sleep more, because it's still early in that way. But thank you so much for everyone to attend, and especially Professor Bai. This excellent talk. Hope to interact with you more in the future.
Yeah, always looking to, and very exciting, inspiring to read your recent papers, and looking forward to read more. So
thank you so much. Yeah. Okay, so
we will talk a little bit later. I will write a recap for your talk. So
thank you, Jingtian. Yeah,
thank you everyone for joining.
Thank you, Professor Bai.
Thank you. Looking forward, possible as well next time.
Thank you.
All right. Bye-bye, everyone.
Bye-bye. Come on.